So the first, like I said, piece is ultimately we're looking at electron configuration. Which is where are the electrons in the atom. But to get there, we need to study the quantum numbers. I briefly mentioned the word quantum mechanics, I think, which is all those calculations you guys were doing. Well, that's part of it anyway. Okay, and these are our descriptors to help us understand where electrons are within an atom. Two analogies I'm going to use kind of simultaneously, but I'm going to describe one of them first. First analogy is, like I was saying, each electron has its own unique position within an atom. So if you have iron, there are 26 electrons in iron. Each of those iron electrons has a specific position that they can occupy, okay, or orientation that they can occupy. And so all 26 of them have a different orientation or area that they can occupy. And so what we need to do is be able to identify where those places are. So we need an address. Okay? So the analogy I like to use here is there's 4 parts to the address. So let's imagine we're trying to find Caleb. And let's imagine that the universe is the United States. And I'm trying to find Caleb. So I'm looking all over the United States, looking for Caleb. Can't find Caleb. Finally, I run into somebody who says, oh, wait, Caleb, he lives in, what would be the next best thing other than the United States? Ohio. Ah, well, that certainly narrows things down. So now, because before I was probably not going to find Caleb ever, would I? Probably not. But now I'm going to Ohio. Have I increased my odds of finding Caleb? Probably. Yeah. Significant amount, right? But what are my chances of finding Caleb now?
Still small.
Still not really high. Would you agree with that? So here I am, I'm trucking around all over the state of Ohio. I'm up in Williams County, I'm down in Gallia County, I'm over in Logan County, there we go. You know where that is?
Nope.
Anyway, so here we are trucking around. I can't find him anywhere. I can't find him. Finally, I run into somebody that says, "Oh, Caleb, he lives in
Central Ohio,
Delaware." So now we're on our third part of the address, or second part of the address, right? Delaware, Ohio. So I come to Delaware. Now I got a pretty much better chance of finding him now, but am I still going to run into Caleb fairly easily? And odds are. Well, let me ask you this. Gracie, have I ever run into you outside of school? Right. So what are my chances of running into Caleb? Not very good yet. They're better than they were before, but still not very good. So I'm running around all over Delaware. I go out to Meyer. I go out to, where do you go in Delaware? Kroger. Which one? Doesn't matter.
Cool Kroger, not Walmart. No, not Walmart Kroger, Cool Kroger.
Yeah, the Walmart Kroger, that was weird.
That was trash. Superior Kroger's the one by Vito's.
Anyway, looking all over Delaware, trying to find, and so I end up at Superior Kroger, and oh, you know what? Caleb actually lives
Looks
on,
Because he actually does.
well, let's imagine that Caleb lives here,
Euclid.
okay?
Something.
There you go, Euclid Avenue, okay? So somebody tells me he's on Euclid Avenue. So now, what are my chances of finding Caleb? Pretty darn good. Now, here's the one thing I forgot to tell you guys. Only one electron can exist in any one address. Otherwise, we would have no idea. We can't have more than one electron existing in the same place. So Caleb's the only one here. So here I am running up and down Euclid Avenue. I'm thinking, hey, I got a pretty good chance here. This isn't that big of a street. And finally somebody says, yeah, Caleb lives at, does anybody know? 289. Interesting. There was somebody that sat in that seat last period that knew that. So 289 Euclid Avenue. I have now found Caleb. There are 4 parts of that address. Okay? Well, as it turns out, there are 4 quantum numbers. We're going to go through each one of them individually, but here's where the other analogy comes into play. I would like you, don't draw anything yet, to reproduce this on your papers, but I would like it to take up about a fourth to a third of the width of your paper and probably almost half of the height of your paper. Does that make any sense?
Yes.
A fourth to a third of the width. So start kind of like what I did. Imagine this board being your paper. Okay? Except you're going to do it there. That's fine, it doesn't matter. Because you can write everything over here if you want.
Ooh, those are very sideways.
So what we just did is made a ladder. Now, if you're going to use a ladder, where are you going to support the ladder on?
The bottom.
The top. Wait.
The bottom.
What?
What's the...
The base. The ground.
Okay, most people say the ground. Okay, good. We'll go with the ground. So basically, we're going to use a ladder analogy here. And the ground is going to represent the nucleus. And this is a 4-rung ladder. Do those M's mean anything to you?
Didn't you say those were moles?
We did when it was something else.
Did you say these were like the electron levels?
The energy levels. And obviously we are going to increase our energy. Okay, now we're going to keep filling in this thing as time goes on. First though, we're going to look at the first quantum number, which is called the principal quantum number. And the principal quantum number indicates the distance of the electrons, I'm going to write of the electrons from the nucleus. Now, in a different color, I'm going to go with green. I should have put A there. My bad. Where did my little packet go? There it is. Okay. And if I write something in green, here's the thing. There's a bunch of analogies we're going to be throwing out there today. The ladder analogy is going to be related to the address analogy here a little bit. When I say quantum numbers, well, I'm going to give you guys both a qualitative, which means we're actually not going to talk about numbers, we're going to use words to describe some things, but I'm also going to show you the actual quantum numbers. You will, anyway. So if it's the actual quantum numbers, I'm going to put it in green. And let me see, part C, the higher the number, the further from the nucleus, which makes sense. So here's our values of n. 1, 2, 3, 4. Higher the number, further from the nucleus. Principal quantum number is easy. This is a thing that you've known for a couple of years now. That's it, though. Everything else we're going to do from now on is going to be new to you, probably. Next, the orbital quantum number. And what this does is designates the shape of the orbitals, kind of a new word going to put in parentheses sublevels. This is the first time we've been discussing this. One thing I forgot to go over with you guys, and I about did it, and then something led me astray. It's not that big of a deal as far as, this doesn't need to be in your notes. But if you can turn to page 107, there should be at least one book at each table. If you can turn to page 107 and kind of share these. Up at the top of page 107, here's the deal. Up to this point, we've talked about energy levels, and I think most people, because you've never been told anything differently, so it's okay, kind of get the idea that, you guys know what a hula hoop is, right? So imagine a hula hoop being spherical instead of just a round ring. So it's still got the little, aren't there beads and stuff in the hula hoop? Right? Okay. So imagine that the hula hoop, the ring, is more spherical now. It's still got that really thin little area where the beads can go, but think of it as spherical. Can you kind of imagine that a little bit? Okay? So I think, and again, you've never been told differently, so there's no reason for you to have thought any differently. So everybody thinks that the electrons only have that one little thin space that they can be in. Does that make any sense? Okay? Well, that's what atomic theory, that's what Bohr came up with for this, the stuff that we are seeing. Each electron is going to be in this area and only this area. Okay? Turns out, though, as the more studies were done, that's not actually true. It's more of a sense of, you guys know what a beach ball is. You ever seen a beach ball with beads in a beach ball? I have, but could you imagine a beach ball with a bunch of beads inside of it? Okay? And if you were to shake that beach ball, where can those beads go? Anywhere within that space, right? So that's more what modern atomic theory is. So when we're defining an energy level, it's not a really thin little region for the electrons to go. It's actually an entire space that they're allowed to exist in. Interestingly, though, if you look at that picture at the top of page 107 there, you'll notice there's a, it's fairly dark in the middle on the one on the left, but as you go further and further from the middle, it gets lighter and lighter and lighter. So if you can imagine each of those little dots representing the electrons, or the place where an electron could possibly be, you'll notice that as it gets further from the nucleus, there's less probability that it could be further and further from the nucleus. Technically, an electron, let's say Sarah is a, what do you want to be? What kind of element do you want to be? She's krypton, okay? Sarah's electrons are going to spend most of their time near Sarah, but technically, some of her electrons could be anywhere in the universe. Now, what's the probability of that going to happen? Very, very thin, okay, very, very slim, but it could possibly be. So where we're going with this is if the electrons could be anywhere, we need to somehow or other define a limit to where we're expecting to see them most of the time, and that's what that little drawing on the right-hand side represents, relative to that one on the left side. So now we're going to determine or define an orbital as a 90% probability region of finding an electron within this volume. So even though they can be anywhere, we still have to, come up with a defined area, and so we've determined to use the 90% probability idea. Yes.
So, but like if I'm talking about level 3 or something, would it start with from the outside of level 2 to the, or is it the whole thing?
Well,
Does that
both.
make sense?
Both. No, it makes perfect sense. And my answer to that question doesn't make as much sense. So when you take your next chemistry course, we're actually going to get into that.
I don't have to worry about that.
You do not have to worry about it right now. Okay? Yeah, we're not going to go there right now. But yeah, that's a great question. There is an answer to that question, but we're not going to have to worry about it in this class.
So I'm just gonna pretend it goes throughout the whole volume and not between the volume of the one before it and the one that it reads?
No, actually, you're going to think more along these lines, and when I finish this off, it's going to make more sense. Okay. Okay. So anyway, there are, as it turns out, 3 different. well, there's more than that. There's a bunch of different shapes that we're going to study, or that are available. We're only going to look at 4 of them, okay? And these are going to be letter coded. So each sublevel has a unique shape. And we're going to call them S, P, D, and F. Those are the 4 that we are going to study in this class. And when you take your next chemistry class, those are the 4 that you're going to worry about. You're not going to worry about anything beyond that. Now, these actually kind of have some specific shapes, believe it or not, okay? The S, and it has nothing to do with the letter S, but is actually a spherical shape. Okay? P, as you're going to find out here in a little bit, is kind of like a dumbbell shape. D, we're not even going to describe, nor F. You'll see why here in a little bit. Now, on page 107, over the right-hand margin, you'll also see, very similar to the analogy I did with the ladder here. Can you guys see a very similar diagram? Okay. The thing that I did not do, you'll find out why here in a little bit, because I need room to put other things in there, because they don't have that there. What happens to the distance between the energy levels the further you get from the nucleus? It gets significantly smaller. So really the biggest gap is between the first energy level and the second energy level. Everything else kind of gets scrunched down a little bit from there. There's reasons for that, which we'll get into later, well, probably won't be this week, but maybe next week. And there's other implications there, which leads to a little bit more what you were talking about. There ends up being an overlap of some of this stuff. Anyway, moving on. Now, we mentioned something about spherical, dumbbell, and a couple shapes that I'm not going to describe. You'll see why in a second. Because if you turn your page over to page 108, you will see the spherical shape that I was referring to. Okay? That would be an S orbital. You'll see in the middle there, you see what I mean by dumbbell shaped? Okay? That is a P orbital. And then you can see a D orbital, right? A representation of a D orbital right next to it. Now, you might think, why don't you just call it like a double dumbbell? Well, if you were to look over right across from that drawing over to page 109, you can see the 5 different D orbitals that there are, and you can see you can't describe all of them that way. Would you agree? Okay, your textbook doesn't show the F orbitals. That's okay. They become quite a bit more complicated from there. I don't think I only got, I think, 1 or 2 books that actually do that. Currently, I don't know where my one. Oh, it's over in Borzak's room. Sorry. Anyway. So anyway, now, there's more to this though. I said that these are descriptors. They're not quantum numbers. So I'm actually going to throw the quantum number at you right now. As it turns out, I said I was going to use green. Where'd my green marker go? As the symbol for the orbital quantum number is L. Obviously, for the principal quantum number, it's N. We already talked about N equals 1, 2, 3, da 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 da. The symbol for the orbital quantum number is L, lowercase l. I always do script so you guys don't think it's a 1, okay? The possible values for L, or the orbital quantum number, are this. 0, 1, 2, 3, through n minus 1. So, they're inclusive, meaning if n equals 1, what is my only possible value for L? Well, n minus 1, which is 0. So what I'm trying to tell you, at the first energy level, we're only allowed to have one sublevel. And that's going to be an S sublevel. Listen, this will not make sense for like a day and a half. In fact, I had a student a long, long time ago in my previous district when I was going through all this stuff. Eventually I get done. I say, does anyone have any questions? Knowing full well that everyone had questions. And finally this student raised their hand. This brave student raised their hand. This would be an Alicia question. Okay? And I said, yes, what's your question? Are you making this up as you go along? It's going to feel that way for a little while. But then it's all going to make sense. So literally, it's
That is such a question I would ask.
So moving on. So now, what if n were to equal 2, the second energy level? Well, if n equals 2, what are my possible values for L? 0
Wait, why 0?
through n minus 1, which is 2 minus 1, which is 1. Remember I said these are inclusive. So you're always going to have a 0, okay, or an s orbital. But at the second energy level, you're going to have a 0 and a 1, okay? So, now, I haven't told you this yet, but the sublevels themselves are arranged according to energy. So the next orbital, which by the way is a p orbital, okay, is slightly higher in energy than the s orbital. Third energy level, n equals 3. What are my possible values for L? 0, 1, 2. Turns out d orbital is L equals 2. So we come up here, S is there, the P is here. Now don't get carried away. The D, go up a little bit and over, we put a D there. We'll fill this in a little bit, okay? And then obviously at the fourth energy level, which I didn't put up there, we could have possible values of L equals 0, 1, 2, and 3. Okay? So we'll go S, P, D. Now, really be careful here. Don't write anything yet. We're going to go up a little bit more, and then over significantly more, and put an F. Now do you see? Yeah, well, anyway. What else do I want to say there? Okay, these are listed, well, as I was saying, each of these is listed in, and I didn't write them that way, but the S is the lowest in energy, the P's are the next highest, F's or D's are next highest, and F's are highest. And you can kind of see that as I wrote it up here. Okay? Little trick that's going to come into play here a little bit later. The number of sub-level shapes is equal to the value of the principal quantum number. What I mean by that is, at n equals 1, how many differently shaped orbitals are allowed?
4.
1. At n equals 2, how many differently shaped orbitals? See where I'm going with that? So the value n not only tells you which energy level, but how many differently shaped sublevels are going to be available. So far, so good. I'm not making this up. All right. See if there's anything else I want to do there. Doesn't look like it. Where am I on time?
You've got like 3 minutes.
Let's throw it out there. Next. Sometimes some textbooks will call this the azimuthal.
Does that say
Make you put the emphasis on the wrong syllable.
Well, what's the
Magnetic. Magnetic. Magnetic.
Spelled
Like I said, sometimes known as the azimuthal quantum number.
Sounds like
Okay.
one of those commercials for like the
This indicates the orientation of these sublevels, otherwise known as orbitals. Be comfortable with both words meaning the same thing, about the 3 axes in space. Yep, you got it. X, Y, and Z. Okay, so the Cartesian coordinates, X, Y, and Z. Yep. Now, do I have a thing here? I do. Okay, so here you go. So there you go. Now, here's what's interesting. I always like to ask this question because it's going to come up in a little bit. No, I'll come over here and do it. Let's do it this way. Could you point out the x-axis, please? Just point out the x-axis. Touch the x-axis. Thank you. Right? Touch the y-axis. Great. John, touch the x-axis. No, I'll have you do it. Touch the x-axis. Go ahead. Excellent, but that's different than what she touched. Why? A different orientation, okay? So where I'm going with this, nothing's X, Y, or Z definitively because atoms are flipping all over the place, okay? Everything's moving around all over the place. Where I'm going with this is we, as humans, to keep track of things, are going to designate X, Y, and Z. But the atoms don't care, the electrons don't care because they're oriented all kinds of different things. Does that make any sense where I'm going with that? We, as a way to speak to each other intelligently, we have to designate them something. So, anyway, as you can see in the books there, the spherical orbital. Really, there's only one way to orient that, such that the origin of the axes is at the center of that sphere, right? That's why the s orbital, there's only one s orbital ever. However, looking at the p orbitals at the top of page 109, you can see that you can orient the dumbbell shape, one along the x, one along the y, and one along the z. See where I'm going with that? We will pick up from there tomorrow. I'm sorry, what? Oh, yeah, I'll make some up or something like that. And then I actually have a key written up already for that. Hi, what's that?
How do you not have the practice?
I don't have a copy. I don't have copies. I don't know. I'll probably do it next period. Lunch.
See you after school.
Okay. Is that a threat or a warning?
Yes.
Mr. Can I come in the 7th period and grab my life study?
Sure. What are we doing 7th period?
Coming in to grab one of your practices.
Oh, okay. Sure.
Scott,
I've seen that. Oh,
Dang.
a conversation just happened.